All right, so how you guys doing today?
Good.
Good, perfect. And it's Friday, right? So we're about to enjoy the weekend. So that's good. All right, so I don't know if you guys watch the Monday and Wednesday lecture on YouTube channel. We're pretty much done with the chapter 6. So I'll move on to chapter 7 today. Chapter 7 is about arcane. Okay, so the very first part of chapter 7, it talks about how important this arcane is in the industry. So this one will not be on the exam, so I'm gonna go very briefly, but you can hear me out just for a few minutes. So if you have a type of like an arcane right here. What they normally do in industry is thermal cracking. Okay. So instead of using some gives free energy as like a potential to move on to the chemical reactions, they just simply use a lot of heat. So they use actually quite a bit of energy in form of heat. So about this 900 degrees. It's quite high temperature. It's a lot of heat energy there. So what happened to those two is usually break apart as two radical fragments over here. So they give us here, here, and eventually they have carbons on the other side break apart, leaving these two at the end. There's a series of the carbons, they're breaking, and they're leaving up those two with this the radical hydrogen here. These two become okay. So why it's so important in industry is there's a lot of things we can do about this arcane group. As you remember, this is the one with the pair of electrons you can find in the pi bonds in the p orbital on these two carbon and this elongated form of a bonding. So you can do a lot of things. You can do a lot of different types of synthetic chemistry with this arcane, and this is why we kind of use as like a building blocks as our desired product name. So the you guys are all like 19, 20, 18, somewhere there. Do you know what I was doing when I was 19 in college? My very first compound I made myself was the olive. I made this when I was 19 or 20, and this is what it looks like. So as you can see, even here, you have even more numbers of pi bonds here, even elongated together. So you can do a lot of different types of chemical reactions, just manipulating the way they can change the bonding or this combined with others. It's a big part of the synthetic chemistry. Anyway, I'll move on. So it won't be on the exam, but kind of shows you why we care about this one so much. Okay, so the biggest difference between alkene and arcane that we talked before is obviously double bond, right? There's somewhere you can find a double bond in the organic compounds that makes this compound alkene instead of arcane. So this is why we sometimes talk about the degree of unsaturated. Do you guys remember this saturations? Probably in Chem 2, and also I mentioned briefly beginning of this semester too. So it's unsaturated means there has to be saturated with hydrogen or something else. So there must be something surrounding the carbons. Then we can say it's fully saturated with hydrogen. That means it's fully saturated with hydrogen. But if you have a somewhere double bond between two carbons, they can be fully surrounded by hydrogen, because this is the way they need to use two pair of electrons instead of one. So, for example, if you had ethylene over here, right? This is over here. So you can just count the numbers of carbons and hydrogen. I mean, you know now how to do 2n, n 2n plus 2 kind of thing, but just count this 2 over here, right? So if it's fully saturated with the hydrogens, there has to be 6 for 2 carbons in a compound. But assume you have a double bond between these two. Okay, the double bond. So now you see the 2 electrons are on from each carbon. It makes the 2 pair of electrons make a double bond. Therefore, there are no more hydrogen will be able to make a bond to the carbon here. So this has now become R-ene. So all you need to do is now EN, not AN anymore. It's ethylene or ethylene, or it's a common name. But so you can do this one. So if you look at this one over here, to make the one double bond here between these 2 carbon, we have to sacrifice 2 hydrogen over here. So yeah, there has to be 6 hydrogen, but there are only 4. So there's a 2 hydrogen missing. Okay. Divide 2 is this one, degree of unsaturation. So degree of unsaturation of this one is 1. That's it. Pretty easy, right? Okay. So whenever you deal with some other compounds with not just the hydrogen but other elements like halogen, or the common element like nitrogen and oxygen, there are certain things you need to kind of memorize, but I will tell you, kind of makes sense probably with this one approach here. So here's the thing, whenever you have like a bromine here, bromo groups here, okay, here. So if you see any like halogen groups like this or here on the carbon, you kind of consider them as just hydrogen, another hydrogen. So because this will also surround this carbon here like as like a hydrogen. So this will give you this chemical formula, right? And you can consider this one as this one for the degree of unsaturation calculation. So this is simply the one carbon should have 4 hydrogen to be fully saturated, right? 2n plus 2, right? So 1 times 2 plus 2 is 4. Therefore, so there's no unsaturation degree there. It's pretty much, but because this is also kind of act as another hydrogen. Sounds good, right? So it doesn't matter. Chlorine, chlorine. Okay. So makes sense, right? Because surrounded by bromine too. That's okay. All right. So the one, this is the first rule. If you see anything in your chemical formula and in here, when you try to calculate the degree of unsaturation, this one added to the numbers of hydrogen, so it kind of works as another hydrogen, so you can do the calculation. Let's do the oxygen here. There's a methanol here. So here's the thing. Whenever you look at the oxygen here, this is a hydrogen group over here. If you kind of consider oxygen also as another hydrogen, it only brings up with also another hydrogen over here. So there is no such a thing like this one. This is negatively charged, but it's a neutral compound. It always has to be following another hydrogen onto this oxygen here. Okay, so that means, if you look at this one over here, over here, right? You have a 4 hydrogen, 1 oxygen, 1 carbon, right? In this case, you can just ignore this one because it's like same as this. Because there's only one bond, there's one element or found in this carbon on this side. Either oxygen or hydrogen, doesn't matter. Because usually oxygen come with another hydrogen, but bromine doesn't have a hydrogen, so we add the number. But it comes with the same numbers of hydrogen here as the numbers of oxygen. So it's just same as this one when you try to calculate for saturations. Because it's all saturated by the oxygen or hydrogen, same thing. So in this case, you just ignore this one. It's still 4, so it's still 0 degree of freedom. Kind of makes sense, right? Okay, good. All right, that's good. This bit tricky one is the mean group. So if you have this one. So this one normally bring 2 hydrogen because it's group 5. They tend to not to be a radical or just try to bring the even numbers of electrons. So they used to have one lone pair over here, a nitrogen group. So this is why they bring up actually 2 hydrogen on this side of the carbon. So think about it. This carbon in this side only covered by 1 nitrogen, but this nitrogen come here with 2 hydrogen, right? So that means you have 4, 1, 2, 5, right? Like this. Okay. In this case, it's covered by only 1 nitrogen, but they give us 2 hydrogen. In this case, you subtract from hydrogen number. So there's 5 hydrogens, but there's 1 nitrogen, so it'll be 4 hydrogen. So you kind of consider this one also as CH. So consider this one still as started by 4 groups. Okay? So it's still 0, not 0.5, not negative 0.5. So this is why whenever you see any chemical formula that has nitrogen, you subtract from it. Okay, let's do a bit of practice over here. Okay, so if you have over here, okay, oh sorry. If you have something like this one over here, what might be the degree of unsaturation here? Okay, so think about it. So if this is fully saturated, right? 2N plus 2, okay? It has to be 8 hydrogen, but there's 6. But in case we ignore the oxygen, right? Makes sense, right? So just ignore this one. We have 2 hydrogens missing. So degree of unsaturation is 1. Makes sense, right? You good? How about this one? Degree of unsaturation will be still. So this 8 hydrogen should be needed. But this is 8 hydrogen minus 2. Right? You subtract. Make sense, right? Okay. One more? One more. Okay. Let's do one more. So how about we have this one? Okay. In this case, still we need 8 hydrogen, but there are only 4. But we're gonna add this number now. This is halogen groups. So let's do 2. It's just you just need to memorize the rule. If it's halogen, add a number to the number of hydrogen. If it's nitrogen, subtract from the numbers of the hydrogen. If it's oxygen, just don't care. just numbers of hydrogen there into saturated numbers of hydrogen minus that antibody. Okay, we good, right? Do you need one more? I think we good, right? Okay, I'll move on. So this is kind of several rules we need to memorize. But as you can see, if you just draw it in the like a Lewis structure, I mean you'll see it like, oh, this is covered by only one nitrogen, but they're coming with the two hydrogen. That's why we need to subtract with number one. Anyway, but you can just memorize it. That's also a good way to solve the problem. So now also we're gonna do some nomenclature for alkene. So it's pretty much the same that we did for alkene. So we're gonna follow the all similar rules. So let's try to some here. So whenever you have the carbon chain here, so 1, 2, 3, 4, 5, 6, will be hex. So this will be hexane, but let's put the double bond right here. Okay, let's put the double bond right here. And you just need to change the ANE to ENE. So we could be hexane. That's all you need to do. So now the only one major difference between nomenclature of alkene and alkene is you also need to locate the double bonds. So that means you have to count the carbon from here, or you can count the carbon in this way as well here. So obviously we want to choose the lowest possible number for the location of your double bond. So it'll be 1 and 2. And also in these two, you also choose the low one among these two, so it'll be N. So we're gonna call this 1 hexane. Okay? This is the way of in textbook it says this one too. Hexane 1 in. I don't know why. A lot of scientists, especially in the United States, they don't really want to use this one. I don't know. This is a new one for sure, but not a lot of people in the United States are not using this one. So maybe you can stick to this one. It's okay. I think this is more clarity for it, but it doesn't matter which one you go with it. Either you put it inside, because this is the way you have a double bond. So they wanted to put it right before where it comes the suffix, but I think either way is fine, personally. So it doesn't matter. So that is the case. So here's the thing. What if you have methyl group over here? Okay. So I know we have learned in alkane we need to give a lowest possible number for your substituent groups, which is one methyl group here. So it would be 1, 2, 3, 4, 5, 6. So in this case, you can do what? 2 methyl, okay? And now it would be 5 and 6, it would be 5 hexane, okay? Here, right? And another way you can do is you could put it here, right? So it would be actually 5 methyl, 1 hexane. Do you guys remember when I did the nomenclature of alkane? You always consider your last name more important, because I don't know in here in the Alabama, but I don't think you can change your last name by your will, is it? But I'm pretty sure you can change your first name in your own way, yes. But that means the suffix is more important for your group name. So to give the lowest possible number for your ENE, which is 1, you can also sacrifice the higher number for the substituent group, that's fine. So this is the wrong one. Okay. This is the major difference between how you're gonna name the compound with a double bond or the single bonds. Okay? Because we consider double bond is more important part of your compound, so we kind of name it this way. We good, right? Perfect. So let's do a little more. Okay. So how about we have two double bonds over here. Okay. If that is the case, it's pretty much the same. But obviously, I'm going to count the carbon from not left to the right, but right to the left. You know why now, right? Okay. But you have two now. So now you have one double bond between 1 and 2. Another, the other one is 3 and 4. So I'm gonna choose this one and this one because these two, this is lower, these two, this is lower, and you have 2. So I just need to put 1, comma, and 3, and hyphen dash, and you're gonna just need to do hexene, but there are 2. So what you need to do, put the hexadiene. So the di means 2. This is you see the hexadiene is kind of hard to pronounce. See the hexadiene. It's the same as like pentadiene, butadiene, because you have like a D kind of sound comes in the middle of your word. You want to have some like a vowel pronunciation to make it more fluently pronounced. So we call this 1,3-hexadiene. Makes sense, right? Okay, perfect. That's pretty much it. That other thing is just fine. As long as you have a lowest possible number for the location of whether you're double bond in your compounds, you can also, based on that carbon number, you can also, locate your methyl group or ethyl groups. And well, for this one, ethyl group would be longer chain, so it would be different. But you know what I mean. So you can have a lot of freedom to change your, not the freedom, sorry, to you know where the substituent group and the prefix will be based on this one. Okay, so I'll give you just one more example here. If you have this one, okay. So this is kind of tricky. Here's the thing. Whenever you look at this one, if you redraw this one, this is skeletal structure. Let me read this one actually. Okay. If you look at this one over here, you have 1, 2, 3, 4, 5. 1, 2, 3, 4, 5, 6. So if you follow the longest carbon chain over here, that's actually wrong. You can do this one because now it's alkene, because you have a double one here. So even though that makes shorter carbon chain, but including double bond is more important, so actually go this way. So this is going to be, let's do this one here now, okay? So this is the longest carbon chain, including double bond. So not 6, but 5. So it'll be, for sure, right? And then you have a 1, 2, 3, 4, 5. So it'll be, do you think it'll be 1, 2, or 1, 2, 3, 4, 5? Obviously. It'll be 1, 2, right? To make a given, okay? So it'll be 1 and 2. We'll give it 1. Because the 1 is lower than 2. Between 1 and 2. And now you can have E and E there. And now you can locate this one as now not in part of your carbon longest chain, but as a substituent group. So it'll be in a prefix now. So this is the methyl, but it's on carbon 2 to count the lowest possible number for the location of the E and E. So it'll be now 2. Okay. 2. That's it. 1. That's the better way to put it. Make sense, right? Okay, we're good. Okay, perfect. Oh, what? Okay, maybe let's move on. So this one more thing, just one more thing. We have the also. You guys remember we did the cycloalkene, right? So obviously, whenever you have the double bond in the ring structure, all you can do is just same cyclo is the same, right? Cyclo. Heg. Now it's going to be hexane. That's all. But here's the thing. Only one slight difference between what we just did from here is this is a ring structure, right? So there's no end. So for cycloalkene, you don't have to number the location of ENE because there's no end. People always assume this is in 1 and 2 carbon, always. So no matter what, either this is going to be 1, 2, or 1, 2. It depends on where you can find the substitution group, but double bond is always 1, 2. So technically, we do this right? But it's a ring structure. Why you bother to put 1 there? It's just always there. We know what it is. Okay, makes sense, right? So if that is the case, Rina is 1, 2. But in this case, I'm going to count 1, 2 in this way to give the lowest possible number for substitution group here. So it'll be 3. So for if you have a monosubstituted cycloalkene, you have this is the way you can number the carbon. So you don't have to number the ENE here, but just substitution group here. That's all you need to do. You don't have to worry about the location of double bond in ring structure because we know where they are. It's just always 1. Makes sense, right? You good? Okay. That's great. That's great. Okay. So let's give it one more example. I'm giving you this example, even though I kind of know you already understood everything. This is kind of an exception. So let me try to draw this. Okay. So here's the thing. This will not be on the exam for sure. Don't worry about this one, but just for your information, you can hear me for about several minutes. Obviously, this is the ring structure, so it'll be cyclo, the 5, right? And it's the ENE. So once again, we don't have to worry about the number because it's always either 1, 2, or 1, 2. So it's a 1. Okay? But the problem is you have a 2 methyl group here, 2 substituent group over here. Okay? So still, you can do your best to give the lowest possible number for the location of these 2 substituent groups. Because as long as you keep these two as 1 and 2, right? You remember this, right? So if you do this, 1, 2, then you can have 2 and 3 dimethyl cyclo and kene. Okay? So this seems quite reasonable, right? But the answer is 1, 5 dimethyl cyclo and kene. So this is 1. Think about it. 2 plus 3 is 5. 1 plus 5 is 6. Right? So this seems like kind of the worst choice for the nomenclature. But the reason why we chose this one is kind of work better for us because it's 1. It's lower than 2. So in this case, we dropped the rule we just memorized before. Like some of these 2 local numbers will be lower is better. Here's the exception. So obviously, once again, I'm not gonna put this on the exam, but I just wanted to tell you this. So in this somewhat weird, like a complex a big molecule with the ring structure with the double or triple bond, you may need to consider sometimes you kind of drop off the one of the common rule to make it more workable name, especially for their certain commonly used chemical reactions. Something like this, but I just wanted to let you know. Okay, perfect. You guys doing so great so far. That's great. Yeah. So that's good. You guys doing so far so good. Very nice. Okay. So now we have double bond. There's something we cannot miss. That is, we kind of briefly mentioned in the previous chapter when we tried to touch the stereoisomers. So you guys remember cis and trans isomers? We kind of somehow talked about this in the previous chapter. But since now we have not just ring structure but the double bond, so if you have the double bond here, it's two carbon here. Obviously, because of this, the pi bonds along with the sigma bond, you cannot rotate it. To rotate this double bond, you have to break it because of the p orbital originally when engaged into this pi bond has to kind of experience a lot of the force to break it. So this is almost impossible to rotate. So that makes these two are different. So if this was a single bond, you could just rotate it to make it this, right? You could just rotate it and move it this. But because this is now double bond, you cannot rotate it. So now we consider these two are different. So we're gonna call this one, cis and trans isomers to each other. Whenever you look at this double bond over here, this is what I normally do. Whenever you have the groups that is same to opposite side over here, you can, this is the trans. Okay. If it's on the same side, okay, we call this cis isomer. So this is the kind of common way to distinguish the two different compounds in a different structure. Well, maybe not structure, but in the oriented and the double bondings and in the position. We can distinguish these two as the trans and cis isomers for this kind of, we call this di-substitute alkane because in double bond you have two methyl groups along with these two hydrogen here that makes either trans or cis isomers. Also, the way I kind of also memorize this one easily is this one. So you have the methyl groups or the other like alkene groups, other R groups over here, and hydrogen here, and here. So if you do this, it looks like a T. So you can just get the trans. If you have R groups on down here, it kind of give you C. So this is how I personally memorize, and when I was in college. So maybe you can do the same, or you can make your own way to memorize. But this is kind of common way to distinguish the two different isomers, cis and trans, by looking at where there's the substituents on each side of the carbon with the double bond. Make sense? So far, okay. All right. So, just one quick question here. If you look at this one over here, can you guess which one will be more stable based on what we learned in previous chapter? When you think about some static hindrance, do you know there's two? So if you think about methyl is a much bigger bulky group than hydrogen here, and if you look at this one here, those two are kind of pointing in the same face, right? on the beside this along with this the double bond here, but this small over there. These two are actually heading opposite direction, right? Well like distributed in the space. Which one do you think will be more stable? Perfect. Absolutely correct. That's awesome. So because of this way, they can slightly more dot from the static hindrance because this bulk here groups over here, but heading opposite direction. But here there's kind of heading almost similar phase. They may interfere a little bit with like discomfort. They kind of need to experience on this side of the space. But this one, well, there's no problem with I can say less problem with the spacing. So normally trans isomer is slightly more stable than this. It's perfect. Great. Okay. So this is the way we can distinguish the two cis and trans isomers. But sometimes you have a bit more complicated situation. We can normally deal with the cis. One example would be this one. Okay. So if you look at the periodic table, obviously among here, here's one thing. Do you guys remember Canning-Gold pre-log convention when we did for the stereoisomers like RNF? So we're gonna do the same here. This one is carbon. This is the hydrogen. So from these two, this is higher than this one. So for Canning-Gold convention for this, the type of alkene, we're gonna do on the ones on the same carbon. So the hydrogen here, these two, not these two, these two. So on the same hydrogen on that double bond, we compare these two groups on the same carbon, this one, and separately this one and this one. Okay. So carbon is higher in atomic number than hydrogen. So this is higher, this is lower. Okay. And bromine and carbon, which one is higher? Bromine is higher, right? Higher. Okay. So if you look at this one, they kind of show you more like higher to higher is what? More like a trans type of structure, right? But as I mentioned before, because of they're different in the priority, but they're not the same elements anymore. So even you do this one, it also kind of shows you a bit of like a cis-like structure too, right? You see that too? So to avoid this type of problems, they use now E and Z here. This is kind of a more frequently used term to distinguish more like the one different shape of the alkene groups with the double bond. So in this case, you have a higher to higher on the opposite direction. We're gonna call this E conformation. Okay. So if we switch, sorry. So if we switch the location here, now it's going to be this way, right? Okay. And now we're gonna go this Z over here. Z configuration for this one. So you can also try to do cis and trans, but you feel like there might be some problem for the people who may look at the name of the compound and see it might confuse. Then you can use just E and Z is better. I cannot pronounce. This is coming from German. Yitadigen and Zizaden. I'm sorry. This is how they pronounce. So this is another way we can do this with the E and Z. Just beside the cis and trans. Technically speaking, they're kind of saying cis and trans is not limited to the di substitute groups or type. But I normally personally prefer this one anyway for any more complicated situation like one we just talked here. Okay. I think. Oh, Okay, so I'll try to cover more example maybe next Monday. So I'll just stop here. But thank you guys. That's it for today.